Chapter 2 will be over standards for measurement. First thing we want to talk about is scientific notation. How do we write scientific notation? It's a way for us to write very small or very big numbers in a compact form, so we don't have to write a bunch of zeros in there and count a bunch of decimal places. So we always write a number between 1 and 10. Smaller than 10, obviously, so it's 9.99 or 9 whatever, and then raised to the power. A power of positive means it's bigger than that actual number. Power negative will be smaller than the number written here. So these are the methods written in instructions for you if you want to go back and refer to it. Let's practice. So in this case here, we have 0.000423. So out of these numbers here, we're not going to write the zeros, but we will write 423. So I'm going to write 4.23, which is why over here is 4.23. Now because the number is smaller than 4.23, we will use a negative. And how many negative? We start counting. So it's 1, 2, 3, 4 negative, and that's why it's negative 4 over here. Okay, so that's the instructions. Let's keep going. In this question here, it says, can we write 353000 through 3 sig figs? So we'll talk about sig figs in a little bit, but let's focus on scientific notation. So whenever you write numbers, we will want to make sure that we write these 353. We don't have to write these zeros. Okay, so 353, I will use 3.53. Okay, and then it is bigger than 3.53, that number is. So how many times bigger? So let's count. It's let's see. So from 3 here, 1, 2, 3, 4, 5. Okay, so I'm going to write down here, my answer is 3.53 times 10 to the power of positive 5. Okay, so my answer should be this one right here. Okay, and in this number, we actually have 3 significant figures because there's 3 numbers that I write down. We don't write these zeros down because they're not significant in this case. All right, so let's talk about significance in a little, in this slide here. We want to talk about measurements first. So anytime we measure anything, we write anything, we always say a number and a unit, a number and a unit, a number and a thing, basically. So 1 cup, 3 eggs, 5 molecules. We always have a number and a unit, okay? Now, when we make measurements in lab, it depends on what we're using. So for example, in this case here, if we were trying to read this thermometer, and this is 20 and that's the way 30 up here. Okay, so from 20 to 30 up here, it says this is 21, but it's actually a little higher than 21, agree? So how would we write that number? We have to estimate it. Okay, so what you always write is, I know it's exactly 21, but it's a little over 21. So I'm going to estimate that last number, in this case, to be 0.2. So I say this is 21.2, but different people could read that number differently. The estimation here could, someone could see it as 0.3, someone could say it's 0.1. So that last number here is uncertain. So we always add that one extra number, okay? So you know to the limit, and then add one more number. So this is the uncertainty number right there. You can't add more than one though. So because we have different instruments in lab, some numbers are going to be, some measurements are going to be bigger in uncertainty than others. Like some of them have more decimal places that are certain. Like in this case, we only have 2 that are certain, and this one is not certain. So let's take a look. And these certain numbers, whatever they are, we actually call them significant figures. So in this case here, if this picture here says, see how this is 22 and is exactly at 22? So I would just call it 22.0 because that number here is estimated. So someone might say, well, it's pretty close. Maybe it's not quite at that line. They could also have easily said it was 21.9. But that's why the two numbers in the front are certain, it's confirmed, but that extra number is uncertain. And then in this case here, if you look at the thermometer, it's graded a little the graduation is a little bit different. So from 20 to 30, there's actually like a lot of little lines there. So there's 21 and 22, and then there's a little line over there, and I can see that that red dot is actually over that 22 line. So we can estimate it to be it's 22.1, because that line, each little stroke there is 0.1, and then you can estimate another number there. So 22.1 is for certain. The extra one here is the estimation number. So in this case here, this thermometer will give you 3 significant figures, and this thermometer will give you 4 significant figures. So it's just different. Sometimes we have graduated cylinders. They also measure differently depending on their markings. So let's talk about sig figs. I call sig figs as a short form for significant figures. So if I say sig figs, it really means significant figures. All non-zeros are significant. So anything that's not a zero will have to count. Some numbers are unlimited sig figs. So what kind of numbers? Like formulas, conversions sometimes are exact, like, or exact numbers like 1 coin, 2 coin. You can't really break those up. And in 1 foot, there's going to be exactly 12 inches. So it's 1.0000000 forever 0 foot equals to 12.0000000. You can see the 0 keeps going inches. Okay, so they have no uncertainty, so they have unlimited sig figs. Zeros are significant when, so there's a few options, but a key point is if you write it in a scientific notation, it is significant. So if you think like, well, that's silly, why would I write that 0 down? Then it's probably not significant if you have trouble trying to decide. So if they're in between non-zero digits, like 75.04, we'll have 4 sig figs because it's 1, 2, 3, 4. You count that 0. And then if they're at the end of a number after decimal point. So like 32.410, this 0 here is significant because it tells you that that last number, the uncertainty is at 0. So 32.410 has 5 sig figs. When they don't count, when they are in front of the number. So like earlier when we were having the 0.00, I guess it was 3, I think it was, no, 423, right? Something like that. And we didn't write the in front numbers. In the same case here, if we were to write it in the same scientific notation, we would have said it was 3.21. So let's kind of write it down here. See, if I wrote this here, I would have written, oh, hold on, erase that. I would have written this as 3.21, correct? And then it's smaller, so how many times smaller? 1, 2, 3 times 10 to the minus 3. And that's how I know these zeros in front are not significant, because I only wrote 3.21. I didn't write 0.00321. All right. And the next thing is when they're not significant, if they don't have a decimal place in a number, it's uncertain. So if you ever have a situation like this and you want to signify exactly how many sig figs, it's really best to write this in a scientific notation. But otherwise, we always assume the 0 is not significant. So in this case, 6920 would be 3 sig figs. If you wanted it to specify as 4 sig figs, you should write it in a scientific notation. So in that case, the scientific notation for this guy should be 6.920 times 10 to the power 123. See how it's bigger? So it's 10 to the power 3. All right. So if it was 4 sig figs, so this means 4 sig figs. If you didn't write it in scientific notation, this number here is assumed to be only 3 sig figs. That's just how it is. All right. When in doubt, if zeros are significant, use scientific notation. See, that's why it's best to learn how to write it in scientific notation. All right. So let's practice. How many sig figs are in this measurement right here? 3.2 inches. So this one should be pretty simple. 3.2 is the only numbers there, so it's 2 sig figs. 25.0 grams. So remember, anything that's after a decimal, the 0 is significant. So if I were to write it in scientific notation, I would write 2.50 times 10 to the power 1. So actually, let's go ahead and write it down. So it would be 2.50 times 10 to the power 1 grams. So I'll write G for grams. So that would make it 3 sig figs because there's 3 numbers in there. All right, 103 people. So it's exactly 103 people. So that would be, can you say 103.1, 103.2? Not really, right? Because it's people. You can just have fractions of a person. So that's why this one would be unlimited number of sig figs because it's an exact number of 103.0000 infinity. Now, 0.003 kilometers, in this case here, see the zeros here are the numbers, the zeros are before, so they are not going to be significant. If I were to write it in a scientific notation, I would write it as 3, let's pick it up here, okay. 3 times 10 to the power of negative 1, 2, 3. Kilometer is km. Okay, all right. So we've all these practice. So next thing we want to talk about is rounding. When it comes to rounding, we have smaller than 5 and bigger than 5. If it's smaller than 5, we round down. We keep the same number. And if it's bigger than 5, we round up. We go up one number. So if they say, in this case here, you want to round at that blue number right here, say if you wanted to keep 3 sig figs, okay? This number is 3 right here, right? So 3 would be less than 5, so we would drop the 3 and keep the 2. So all these numbers here can just disappear and we can just keep 53.2. And then if we wanted to round to this, the third number here in 3 sig figs, and it's 11.789, but 8 is bigger than 5, so we're going to round the 7 up to 8 and keep 11.8. All right, so next thing is let's practice with rounding. So it says here they want to round this to 4 sig figs, so that means we have to keep 4 numbers, and that 7 is going to have to disappear. Now that 7, is it higher or smaller than 5? So I would say it's higher than 5. Okay, so we're going to go up on this number, so we'll drop 7 off. 3 is going to go up to 4, so our answer in this case would be 79.14. Now, the next thing is let's round this one to 3 sig figs. So that means we have, this is 1, 2, 3, so the zeros in the front here don't count, okay? Because obviously, even if you wrote it in scientific notation, you don't write that number, correct? So if it's 4, 3, 4, 5, when we want to round it to 3 sig figs, we would stop at this 4 here. But since this is 5 and higher, we will round up. So it would be 0.0435. Now, if we wanted to write this in scientific notation, we can actually practice too. Let's do that. In this case, I would write 79.14, so 7194, all the numbers are in there, and we put a decimal right there, times 10 to the power of 1. Okay, now this next one, if we wanted to write 435, I would write 4.35 times 10 to the, it's negative. Okay, let's count how many negative. 1, 2. So negative 2 right there. All right, next one. 136.2. We wanted to 3 sig figs here, so we're going to cut it off at 6. And since 2 is less than 5, we'll keep at 136 right there. All right, let's keep going. If we want 2 sig figs over here, we would do 1, 7, and we'll stop at the 9 because they want just 2 numbers. So it would be 1, 7, but since 9 is bigger than 5, it would go up to 1, 8. So hopefully that makes sense. Let's practice writing it in scientific notation here, actually. So 136.2 rounded at 136, so we get 1.36 times 10 to the power of 2. And then this one is smaller, so it's 1.8 times 10 to the, see how it goes to 1, says 1 time to that number right there, so it's negative 1. All right, next slide, I think we're going to start practicing calculations with sig figs in it. So we can only keep the smaller number of precision that we have, so smaller sig figs for multiplication or division. And if we are doing addition and subtraction, we actually keep the smallest decimal places. So for example, if you're multiplying or dividing, in this case, I have 3 sig figs here, and I have 2 sig figs here. Even though we put this in a calculator, we get a bunch of numbers. Technically, if we were limited by our instrumentation, we only know it to the accuracy precision of 2 sig figs right there. Okay. So I would actually keep 87 as my answer. Now when we do calculations, a good practice is actually to not round until the end. Just keep your numbers on the calculator and remember how many sig figs you need. A lot of times I actually underline how many sig figs I need. Like for example, if I were to write this is 3 and that's 2. So I would know I need 2 sig figs. I actually underline the second number, reminding myself that I need to keep just 2 numbers. All right, let's practice. So if you were to do this calculation, you can easily do this on your calculator. 12.18 times 5.2 and then divided by 13. See, this has 4 sig figs, this one has 2, this one has 2. So my answer, even though it comes out like this, we really should only keep 2 numbers, 2 sig figs. So if you were to round 4.872 to 2 sig figs, it would be 4.9. So I would pick A as my answer right there. All right, so I mentioned this earlier, we were talking about addition and subtraction. We keep the smallest decimal places, okay? So if I have adding 136.23 and 79 and 31.7, we look and see who has the smallest decimal place. In this case, it's 79, it has nothing. So we keep no decimal place, so we would keep just 246, the third number right there. And since it's 93, we will round up to 247. So let's practice this one. 142.57 minus 13.0. So this has 1 decimal place. That one has 2 decimal place. So we would keep 1 decimal place in our answer. Even though the calculator will tell you there's 57, we'll keep 1 decimal place. And because this 7 is higher than 5, we'll keep 129.6. So I would pick answer B here. right here. So this next one, we're going to do a mix, okay? So we have to do 12.18 minus 5.2, and then you have to get that answer and take that and divide by 10.1. So over here, they wrote 7.0 here. You can actually, I would actually just keep 6.98 and put it 6.98 over here, divided by 10.1. But let's take a look at one step first. We do one step at a time. So we do the top part first, right? So 12.18 minus 5.2, the answer of my calculator gives me 6.9, okay? But because I know I can only keep two numbers, I'm going to write down 6.98 and then I underline 9, telling me, okay, remember when you get your final answer, you actually are stopped at 2 sig figs right there. So then even if you put 6.98 over here divided by 10.1, you get a number, and you only keep two numbers there, and you actually get the same answer because you remember you have to keep 2 sig figs. So my 2 sig figs would be right here. So I would round to 0.69 because 3 is smaller than 5. So I would pick D as my answer right there. All right, so let's try. Here's another one. So it's all plus and minus, so you just keep decimal places in this case. So we have to keep our decimal places. So let's try looking at the math together. You would do 1.6 plus 23 minus 0.005, and then you get 24.595 if you did it on a calculator. Okay, and on my calculator, it will tell me this answer, but then we gotta decide, well, where should I stop my final answer? So I would say, since this is all plus and minus, we'll keep smallest decimal place. That means this guy has no decimal place, and actually keep an answer with no decimal place. So if I were to keep this answer, and I would keep it at right here, because there's no decimal place, I would actually pick my answer to be just 25. Which means it's 2 sig figs right there. Okay. So now the next thing is we want to talk about measurements of metric system. So metric system, they give you the SI units, standard measurements that what we use commonly. In this case, the SI unit for length will be meter. And then for mass, we use kilogram. Temperature, we use Kelvin. Time, we use second. Amount of substance, we use mole. Electrical current, we use ampere. We will be focused on most of this. You don't really see amps until we learn electrochemistry a lot later on. So, but obviously there's other units that we use as well. Let's take a look at prefixes for our metric units. Now you're going to want to memorize this, okay? So let's put a note here and it says memorize this. Oops. All right. So we want to go giga. We've heard of giga, like gigabyte, so it's the same, similar. In gigabytes, it's like actual different numbers, but for us, our giga is going to be 10 to the power of 9. Our mega is 10 to the power of 6. So 6 means 6 zeros, 9 means 9 zeros. So 10 to the power 3 for kilo means 3 0. Hecto is 10 to the power 2. Deca is 10 to the power 10. And then obviously there's just the 1 there to the power 0. And then deci is when it starts to get smaller. Deci is 0.1 or 10 to the minus 1. Centi is 10 to the minus 2. So these are smaller than 1. Those are bigger than 1 numbers. And then the next one, I want to memorize this. After centi, we have milli, 10 to the minus 3. Micro, 10 to the minus 6. So whenever it's 10 to the minus, it's just how many decimal places, like 1, 2, 3. So it's 3. And then 1, 2, 3, 4, 5, 6. That's why it's 6 right there. So for nano, it's 10 to the minus 9. Pico is 10 to the minus 12. Femto is 10 to the minus 15. So you're definitely going to want to memorize these guys. Okay, so on the previous slide and this slide, I want you guys to take a break here, make some flashcards, and start memorizing these prefixes. Now, so some of the common measurements that might be good for us to remember. 1 meter has 100 centimeters, and 1 centimeter has 10 millimeters, so as 1 meter is 1,000 millimeter. Okay. 1 kilometer is going to be 1,000 meters, but we already knew it says kilo on a previous slide that kilo means 10 to the power 3 or 1,000. So it really means how many meter? That's 1 kilometer, 1 times 10 to the power 3 meters. Okay, and then these measurements for English units here, it's not necessary to actually memorize every single thing. If you had to do homework or whatever, you can always refer to our slides here. And if it's on a test, I'll make sure you guys are provided with the English conversions. I do want you guys to memorize all the metric ones though, okay? And obviously, this is pretty common too, so we gotta, I don't think if you don't remember, that's okay, but this one's pretty common. You do it so much, you end up memorizing it by accident. So 1 inch is going to be 2.54 centimeters. All right, let's talk dimensional analysis, how we can use it to solve problems. So here's a problem for you. How many seconds are there in 1 week? So we know that 1 week has 7 days, 1 day has 24 hours, 1 hour has 60 minutes, and 1 minute has 60 seconds. So you can take a second here and put it in your calculator and see how you would do that. Obviously, you'll go from week, correct? You go from week and then you convert it to the next smaller number to days. And then from day, you convert it to hours and then to minutes and then to seconds. So then you just figure out how you want to do this. You probably say, oh, well, I'm just going to multiply the numbers together. That's correct. So I want to show you how I would write it in dimensional analysis. Okay, so I would go 1 week. Okay, and then instead of writing multiply and divide, I just kind of draw lines like that because then it's a lot easier than trying to write multiply, multiply, multiply every time. So anything that's on the top will be multiplied, anything that's on the bottom will be divided. Okay, so 1 week, the next unit I want to convert to is to 7 days. 1 week is 7 days, right? And I know that 1 week and 7 days is exactly the same. So whether or not I write 1 week over 7 days, because it's the same thing, or I write 7 days over 1 week, they're all going to be the same thing. Okay, so in dimensional analysis, I'm going to pick where the week is going to be canceled out on the bottom and the days is going to go on top. So the unit that you want stays on the top and the one you want to cancel out goes on the bottom. So I will obviously put 7 days to 1 week here. Okay, and then we go to the next one. From days, I want to go to hours. So I know that 1 day is 24 hours. So I'm going to cancel out the day. So 1 day goes on the bottom, has 24 hours, goes on the top. And then the next thing I want to do is I want to do to 1 hour to 60 minutes. So 1 hour has 60 minutes. And then we can do 1 minute has 60 seconds. And then we get our answer, correct? So if you put this all in your calculator, you get a really big number and it's 604800 seconds. If you put S, it's basically the short form for seconds. It's a unit abbreviation right there. Okay, so that's how you would do it. Remember, we do this because we want to cancel off the units. So if you look here, the week and the week cancels off. So now your answer is in days. The days and the days cancel off. Now you have your answer in hours. And you keep going, hours and hours cancel off. You have your answer in minutes. You keep going, answer in minute and minute cancel off. Your final answer will be in seconds. And then you take your numbers on the top, multiply with all the numbers, and divide all the numbers on the bottom. Okay, so you would do 1 times 7 divided by 1 times 24 divided by 1 times 60 divided by 1 times 60 divided by 1. Or I just usually ignore the ones. You can do 1 times 7 times 24 times 60 times 60. Okay, now if you had numbers on the bottom, you can multiply everybody on the top and then divide everybody on the bottom. It doesn't have to be up, down, like that. So we'll get more examples as we go. So since we've been showing you dimensional analysis, here's the same idea. We know that 1 kilometer and 1,000 meter is interchangeable with 1 meter or 1 kilometer. And we use this to our advantage. You can either arrange it like this or like that to use for our calculation to change units. So we want to do 2 meters, 2 kilometers, then we do meters down on the bottom so they cancel off, and then kilometer on the top. So basically like what I've been showing you on the weeks and seconds. Alright, so we're going to use maps like this to solve a lot of problems actually, probably the whole entire semester. And we call this the dimensional analysis method. So here's another couple examples. Okay, so 215 centimeters to meters and 125 meters to kilometers. So let's do this one first. So they wrote down 1 centimeter is 100 centimeter and 1 meter is 100 centimeters. So if you knew that, you can write it like that. Or if you memorize it straight from the table, there's actually another way we can write it. We know that 1 centimeter from the table means 1 times 10 to the minus 2 meter. And then we could also write 215 centimeter, and then we do this, where I'm going to put my centimeter on the bottom, so 1 centimeter is on the bottom, 1 times 10 to the minus 2 meter goes on the top, and you'll see you get the exact same answer of 215 meter, 2.15, right there. Okay, so that's the same thing as over here what they have written. Once you do it a bunch, this starts to become common, but when you're still beginning, if you're memorizing, that's okay to use this way too. They both give you the same answer. Okay, all right, the next one is 125 meters to kilometers. This one is pretty simple because it is getting bigger. 1 kilometer is 1,000 meter. So you put the meters on the bottom, cancel it out, you get 0.125 kilometers. So the next thing is how many micrometers are there in 0.03 meters? So I put this chart here for you, but obviously you want to definitely memorize this. But we see micro is 10 to the minus 6. Okay, or 1 times 10 to the minus 6. It's really the same thing. So if we're going to use that conversion here, so let's write it down. 1 micrometer is 1 times 10 to the minus 6 meter. Okay? Let's erase that right at meter. Alright. So let's use our conversion. We'll have 0.03 meters. So who should I put on the bottom and top? I'm going to put meters on the bottom. So 1 times 10 to the minus 6 meter on the bottom, 1 micrometer on the top. Okay? Now you do this in your calculator, and you'll see we get an answer that makes it bigger. Okay? You will get 30,000. You see how this is one sig fig here? This is also one sig fig right there. So our answer 30,000 is going to be A right there. A is our answer. So here's another problem. How many feet are in 250 centimeters? So from my conversion units here that I have posted, you go from centimeters to inches, and then you can see that inches can go to foot right there. So that's what we would use. We go 250 centimeters, 1 inch, 2.54 centimeters, because you want to cancel the centimeters off, and then 1 inch, and then cancel the inch off, 1 foot to 12 inches, and you get your answer. In this case, we keep 8.2. Technically, it's just, if it's just 2 sig figs, you would have kept 8.2 feet, because we're not really sure if this was significant. If it was, they should have written in scientific notation, correct? And this number has 3 sig figs, okay? So how many meters are there in 5 yards? I would go from yards, and then we would go to from yard to feet, and then 1 foot to 12 inches, and then from 1 inch to 2.54 centimeter, and then from centimeter we got converted to meters, okay? So let's write it down from the table that you should be memorizing. 1 centimeter is 1 times 10 to the minus 2 meter. Okay, now we can follow the conversions they have here, because they remembered that 1 meter is also 100 centimeters. If you can remember that, great, you can use this conversion right here. You see how they cancel off the yards, and then they cancel all the feet, the inches, and then the centimeters to get the meters. But I can show you how I would write it out too, okay? So I would start with 5 yards. And then since I'm gonna start using abbreviations, so yard is YD, and then I'm gonna do 3 feet is in 1 yard, right? And then I'll do 1 foot is 12 inches. And then from my 12 inches, I can go to centimeter. And then my centimeter, I'm going to go to meter. So 1 centimeter is 1 times 10 to the minus 2 meter. Let me continue this line. All right, and that equals to, if you put it in a calculator, you should get the same answer. And in this case, it would show you 4.57. Okay, now 5 yards here is going to be exactly 5 yards if they tell us, unless they specify this was an exact number, then we really should be keeping 1 sig fig here. But obviously the answer choices that was given here, we have a 4.57, so we would pick that one. They should have written 5.00 if they want to see how the answers all have 3 sig figs. So the accurate way to do this is they should have said 5.00 yards. So let's write it down. 5.00 yards. And then you would get 4.57. All right. So if you ever have to do volume, like cube, centimeters cube here, and you have inches, you gotta remember that inch and centimeters, if you're doing cubes of it, you can actually cube everything, the number and the units, okay? So we will cube the whole entire term. So in this case here, if you get an answer of 2.20 times 4 times 6 inches, you get 552.8 inch cube. And then we want to take this inch cube here to convert to centimeters cube. Then you use this conversion in here, but you cube everything. So when you do your calculations, you actually do 52.8 times 2.54 or cube, or you can just do times 2.54 times 2.54 times 2.54. Just do it 3 times. That's what cube means. And then you would get your answer 865 centimeters cube. Okay? So try it out on your calculator, make sure you can get it. So we want to talk about mass a little bit here, and a little bit of a difference between mass and weight. Mass is amount of matter, so we measure on a balance, and weight depends on gravity. But mass is independent of location, and weight is not, so we always use mass in our calculations, okay? Mass is a standard measurement of the metric system, and our unit is actually going to be kilogram, the SI unit. But you'll see, depending on what we use, sometimes we use kilogram, sometimes we use grams, sometimes we use micrograms. It really depends on what we're weighing out. All right, so conversion from English to metric. So 1 kilogram is 2.2015 pounds. Again, if you need this, I'll give you the conversion from metric to English. But you need to memorize again these. Well, you should have memorized it, and you'll see how we have kilo. We memorized it from the table from prefix, and then we have the regular gram, and then we have deci, which is smaller, centi, which is smaller, milli, which is smaller, micro, which is smaller. You see how it's like 10 to the minus? It's exactly the same as that chart we had, but now we have grams. So no big deal. We can always change the grams to seconds, to meters, to liters, anything like that. But if you memorize the prefixes, it'll go a really long way. So over here, we want to do 3 grams to kilograms. So we need to know the conversion. 1 kilogram is 1,000 grams. And remember, we can write it either way. And we choose the method that we can cancel the grams on the bottom and kilogram, the unit that you want, on the top. So you get 0.343 kg here. So the next question is, how many centigrams are there in 0.12 kilograms? So this one goes a little further because we got different units here. We got kilograms. I would turn kilograms to grams, and then from grams to centigram. So you have to do a few steps there, and I provided this chart here for you, but when it comes to the test, you want to make sure you have memorized all of this stuff. Okay, so let's write down what we need to know. We have kilograms is 1,000 gram, and then centigram is 10 to the minus 2 gram. So we will start with 0.12 kilograms. Okay, and then I want to convert it, so kilogram turns to grams first. So I'm going to put the grams on the top here and then kilograms on the bottom. So I know that 1 kilogram is 1,000 grams. Okay, that's my conversion for the first step here. So you see how kilogram and kilogram cancels off. My answer is now in grams, but that's not enough because they want it in centigrams. So if you look here, centigrams is 10 to the minus 2. I like to write 1 times 10 to the minus 2 just in case you forgot there's actually just 1. We do 1 centigram is 1 times 10 to the minus 2 grams. Right there. Okay, if you put this in your calculator, if you put it in correctly, you should get your answer. And it's going to be 1.2 10 to the power 4 because it's 12,000 on your calculator. Okay, so we want to keep 2 sig figs here. So it's 1.2 times, see how? 1, 2, 3, 4. So it goes 10 to the power 4 because it's bigger. So our answer would be B. And then we want to talk a little bit about volume. We can use to measure volume, we have graduated cylinders, which you'll use a lot in lab, volumetric flask. And then we have a burette you'll use for titrations. We also have pipettes and syringes. We use pipettes too, but we don't use it as often as graduated cylinders and burettes. So we typically in lab will use the units liters or milliliters for our volume, and you want to remember that a liter is a cubic decimeter, so of water at 4 degrees. So that's the definition, but you don't have to worry too much about it. 1 liter has 1,000 milliliters. That's something that we always have to remember. So here are common ones, like we just mentioned. 1 liter is 1,000 mils, and 1 mil is 1 centimeters cube. Always remember that. So a centimeters cube and milliliters are going to be interchangeable. So have this memorized here, okay? You don't need to memorize the course. I'll provide that for you if you need it. So if you have a question that says convert 0.345 liters to milliliters, then you need to know the conversion is 1,000 mils to 1 liter right there. So again, remember, memorize this and that. Alright, so how many milliliters are there in a cube with sides measuring 13.1 inches each? So you would need to do 13.1 times 13.1 times 13.1 inch cube and convert it to milliliters. So what I would do is I would remember that 1 inch is 2.54 centimeter, and then once you get centimeters cube, we know that it's 1 centimeter cube is 1 milliliter. Okay, so I would do 13.1 inch times 13.1 inch times 13.1 inch, right? So let's see what we get there. I'm gonna get a bunch of numbers, so let's just write it all down. 2248.091. You can do this along with me on your calculator as well. Okay? And then we'll take all that number, and I'm going to remember that I'm actually only going to keep 3 sig figs. So I underline my third number right there. And I'm going to take that number and I'm going to start converting it over, okay? So let's write it down. 2248.091 inch cube. And then we're going to convert. And remember, we're keeping 3 sig figs, so underline that number. 1 inch is to 2.54 centimeters. So since I'm cubing this and cubing that, I have to cube that too. And 1 cube is just still ones, right? So it doesn't really matter. So it's 2.54 cube, okay? And then once you do that, you have the next conversion is 1 centimeters cube is to 1 milliliter. All right, and then we take this times 2.54 cube, and I get my answer 36839.61. But remember, it's a long number, but I'm only going to keep 3 sig figs, remember? So in this case here is 36839.61109. So it's such a long number, and I'm going to keep just 3 sig figs here. So actually the answer choices here should have said 368, not 369, because I'm actually going to round it to 368. Okay, so sometimes they have little typos with rounding. But in any case, if you had to pick an answer, we would pick the answer that's closest. So it would be 3.68 times 10 to the power of 4. See that? Because it's 1, 2, 3, 4. So I would pick D as my answer here because that's the closest one. Okay, let's go to the next one. Now we want to talk about percent. So what is a percent? It is basically a part that you're interested in divided by the total parts. So everybody on the bottom. So so the formula here to get percent is what you're interested in over everybody times 100. So let's take a look here. If there's 25 flowers, red ones, 33 yellow flowers, and 22 white flowers, what is the percentage of the red flower? So they're looking for the red, okay? So we got to put the red, which is 25, on the top. And then we got to put everybody on the bottom, which is 25 plus 33 plus 22 on the bottom, and then times 100. So you took 25, 33, and 22, you add up, you get 75. 25 divided by 75 times 100 gives you 33%. So that would be the percent of red flowers. So in chemistry, we always look at mass percent. That's one of the really common ones that we use. So mass percent is just really percent, but in grams, okay? Or kilograms, anything that's mass units. So typically we use grams though. So mass of what we're interested in over mass of everybody times 100. That gives us mass percent. And any mass units can be used because if you use gram here, you could use grams here. If you use kilograms here, microgram here, it cancels out, so you still get percentage anyway. So as long as you use the same unit. So let's try an example here. It says here we want to find mass percent of nickel and oxygen separately. So since there's two things in here, we have nickel oxide, that means it's nickel and oxygen. If you find just the nickel, then you can just actually take 100% minus the nickel's percent and get the leftover instead of calculating the other formula. Okay, so I'm going to show you how to do this one. We'll do this together. So over here, first of all, let's do mass percent of nickel. So what I want to do is we are going to take 14 grams of nickel because it says there's 14 grams. And then you have to divide it by the total, which is 14 grams nickel plus 7.64 grams of oxygen. Okay? And then you, whatever this answer is, you put that in and then times 100. So 14 plus 7.64, this here actually makes 21.64. So if you take 14 grams over 21.64 grams, you see how the grams cancel off? And then times 100, you will get 64.695. So 64.695%. So that's a lot of numbers, but you see how there's four numbers here and four numbers here. So 4 sig figs, I would want to keep 4 sig figs here ideally. So I would actually say 64.70. Okay, so if we were to keep sig figs here, 64.70%. And then you can just pick whatever left over is the number for oxygen. Since there's two parts, percent of nickel is 64.7, or we can round out to 65%. So if there's 100% total minus 65% of nickel, the leftover percentage would be for oxygen, and oxygen's number would be 35%. Okay, so in that case, we actually would pick the answer C. Okay, and if you did the work for oxygen separately, it would look like this. It would be 7.64 grams of oxygen divided by the total gram, which is 21.64 grams, times 100%. And then you will get the same answer. You'll get about 35%. Next, we want to talk about temperature, and how to measure it, how it has to do with heat. So heat is the flow of energy. Heat has to do with energy calculations. It changes because energy can flow from one object to another, so the temperature can go up and go down accordingly. Temperature is just a measure of how much thermal energy the object has. So temperature is a measure of thermal energy of a system, and thermal energy is a form of energy, including basically it's like movement of small particles in there, and it warms the matter up. All right, and then obviously heat. So there are a few terms here. So when we say heat, sometimes I use the symbol Q for heat. Okay, it means the same thing. So just keep that in mind. And then temperature is just, a lot of times we just use capital T for it. Typical unit for temperature, SI unit is Kelvin, but a lot of times we also use Celsius. We do sometimes occasionally have conversions to Fahrenheit. We can practice that too. So see, there's Fahrenheit over here. Okay, that's what we use in everyday measurements here, but in lab we will be talking about Celsius and Celsius temperature and Kelvin right here. So you want to remember that 0 degrees Celsius is 273.15 Kelvin, or sometimes we just use 273. And Fahrenheit, we obviously know 0 degrees is 32 Fahrenheit, but 100 degrees Celsius is going to be 373.15 Kelvin. The size a scale for Kelvin and for Celsius is actually the same size. You see how it goes from 0 to 100, from 273 to 373. So from 0 to 100 is 100 numbers. 273 to 373 is also 100. So the scale size of Kelvin and Celsius is the same, but it's different from Fahrenheit. So you gotta be careful with that. Fahrenheit actually has 180. So what is 100 degrees? It's actually 180 degrees in Fahrenheit. So it's completely different. We also have a special name. The lowest temperature possible on the Kelvin scale is called the absolute zero. Absolute zero is negative 273.15 Celsius. And that would equal to 0 Kelvin. So that's 0 Kelvin. All right, so here's the formulas for our temperature conversions. So right here, you see that Kelvin is just a Celsius plus 273.15. That's pretty simple. Need you guys to memorize this. This one here, not as important, but once you do a few, you start memorizing. Is Fahrenheit is 9 over 5 Celsius plus 32. So it's kind of easy to remember because it's 9 to 5, like that's kind of how I see it. But just if you need this, I will provide this for the exams for you, but you have to know the conversion between Celsius and Kelvin. Okay, so here's a question to say, why does 723 Celsius convert to Kelvin and Fahrenheit? So to do it to Kelvin, we would put the 723 Celsius right here, and then plus 273, you get 996 Kelvin here. So in this case, because the number started without decimal place, our answer will also have no decimal place here. For Fahrenheit, the same thing. If you want to put 723 degrees Celsius where the C is, so in this case, that's where it goes. So Fahrenheit equals to 9 over 5 times 723 plus 31. So do this one first, get a number, and then add 32, and you get 1333 Fahrenheit. So here's another example here. It says, what is the temperature if 98.6 degrees Fahrenheit is converted to Celsius? So obviously we want to use the Fahrenheit and Celsius conversion equation right here. And let's go ahead and plug it in. And just for fun, we're going to go ahead and do it to Kelvin too after that. All right, so right now we have Fahrenheit, so it's 98.6 F equals to 9/5, whatever our Celsius answer is, plus 32. All right, the next thing is, let's go ahead and work on the algebra here. So I'm going to do 98.6. I'm going to drop the units for F here. And then I'm going to do both sides minus 32 equals to 9/5 Celsius. Okay, so 98.6 minus 32, you get an answer at 66.6 equals to 9/5 Celsius. And then to get the Celsius answer, let's rewrite it nicely. Celsius answer would be 66.6 and then we got a times 5 and also divide by 9. So that's just algebra right there, okay? And that should give us our answer. And my answer is going to be 37 degrees Celsius. Exactly 37. So that would be my answer A here. And if I wanted to change 37 degrees Celsius to Fahrenheit, I would do this. 37 Celsius plus 273.15 would give me my Kelvin answer. In that case, it would be, I'm not going to keep the decimal, so 310 Kelvin. Next, we want to talk about density. Density is basically mass divided by volume, the ratio of mass to volume here. It's a physical property, and we'll learn that density doesn't change with the compound, so it's actually called an intensive property. Whether you have a little bit of the stuff or a lot of the stuff, the density stays the same. Just think about water. A small amount of water has the same density as a big amount of water. So that's what intensive property means. So over here, the typical units for density we use is grams per mils for liquid, grams per centimeters cubed for solids, and then grams per liter is typically for gases. So volume of liquid does change as a function of temperature. So density is given for a specific temperature, but you don't have to memorize that, like what density is at a temperature. We usually will provide that to you if you need it for calculation. So it says here water at 4 degrees Celsius is 1.0 grams per mil, but then if you warm it up, it's actually a little bit different. But typically we just keep it as 1 grams per mil for our density of water when we calculate stuff. So obviously when different things have different densities, the amount of stuff that you see actually looks different. So what does that mean? So if they're all same volume, because gold is so much more dense than sulfur and then water, gold actually will weigh a lot more. And then if you wanted everybody to weigh 10 grams, there will be a smallest amount of gold, small volume of gold will make 10 grams. You can take more sulfur to make 10 grams and a whole lot more water to make 10 grams. So let's practice here. If we wanted to do 323 grams of a substance and it occupies 53.0 mils, and we want to find density, all you do is take the grams, the mass, divided by volume. So 323 grams divided by 53.0 mils. We'll keep our answer in 3 sig fig, and you get 6.09 grams per mil. It's just whatever the units here, you write that down there. So over here, we have the density of gold is 19.3 grams per mil. That means every time there's 1 mil, there's 19.3 grams. Okay? And then what is the volume of 25 grams of gold? So one important thing is when you see this here, you gotta remember that the density number means 19.3 grams can be found in 1 mil. So if you were doing your conversion calculations, you could do 19.3 grams divided by 1 mil, or you can write 1 mil is 19.3 grams, just depending on what you need for calculations. And you can see down here, we actually use 25.0 grams. And then we gotta cancel the grams off, so we put the grams on the bottom, 19.3 on the bottom, 1 mil on the top, and you get your answer of 1.30 mils. And we do keep 3 sig figs here. This 1 mil is exactly 1 mil, so it has unlimited sig figs because it's 1.0000000 to infinity. So let's do our last question here. The last question here is what is the mass of 1.50 mil of ethyl alcohol? This is ethanol, a common alcohol that we can find in drinks. And then density of alcohol that's given is 0.789 grams per mil at 4 degrees Celsius. So you just use this number to calculate. All right, so we want to find the mass, which is in grams, okay? So let's go ahead and start there. So remember, when you write density, it says 0.789 grams per mil. That means is 0.789 grams can be found in 1 mil. Okay, so if I have 1.50 mils of alcohol, I want to convert it to grams. That means I'll put the mils on the bottom. 1 mil is 0.789 grams. And then we can cross off the mils. And our answer here, if you put it in the calculator, you actually get a long number, 1.1835 grams. Now, you see here, my question has 3 sig figs. The density has 3 sig figs. So my answer here should only have 3 sig figs. If it's 1.1835, 3 is less than 5, so I'm going to round to 1.18 grams. So my answer here should be B. And this is the end of chapter 2.